Hello, everyone. We have introduction to ParaView scripting today as a topic. We're going to go through automation of visualization, extraction of data, and building reproducible workflows with ParaView scripting. Today, I would like to ask you to turn off the cameras, to mute your microphone. If you're not speaking, also write your questions in the chat. We have a live chat during the webinar. And we have also prepared a survey, a poll, sort of questionnaire in the live chat to, let's say, collect your background to understand your background a little bit better, so we can shape the webinar a little bit better. So today we have, I think, the second time in a row with Cesar, a ParaView topic as a webinar. It's sort of a part two of the previous webinar, but I can see that most of you guys have not participated in the first part, so you're kind of new to that webinar today. But I think it's fine. I think we are also prepared for that use case. So I will quickly start with the brief introduction. What is Wired White? What we do and why we do it. So basically, Wired White is an engineering platform. It's an engineering community that we have built to support the electrification worldwide, and we have also some useful engineering tools integrated into the platform, provided to our platform users so that they can, so in that way we can enable, let's say, this global cooperation and knowledge sharing by using that platform, by providing it to others. And basically, we have two major user types. First one is the customer, and the second one is the partner. So customer is basically a user that can receive a private tutoring and mentoring. The customer can take online courses. The customer can participate in these sort of online webinars that we have in now. The customer can read technical articles from experienced engineers, from our content creators. So basically, the customer is a sort of a not very much experienced engineer that is gaining experience in that field, and it can be also a student finishing his master's degree, or even a PhD student. So this is what we call customer. It can be also a industrial, let's say, customer, a company behind a legal entity. So this is what you can imagine under customer. And once the customer started gaining experience, started being more experienced in the engineering field, getting some courses, getting some tutoring. So he's going through that gaining experience phase. He can transfer to become a partner. A partner basically is a experienced engineer. It's a content creator. It's an author. It's a webinar speaker. So basically, it is a experienced engineer that can be a private person. It can be also a legal entity, a company, an agency that can use our platform and can provide the tutoring, the mentoring. The partner can sell, of course, obviously create first and sell online courses. The partner can be a speaker during the webinar, and the partner can also join in industry projects with us, or with directly with the company from the customer side. So basically, this is what we call partner. Cesar is also a partner of us, our platform member, and the tools that we provide also on the platform are mostly useful for engineers. So these are For instance, we have this video conferencing tool inbuilt that we are using now during our webinar. We provide it as a built-in feature to our members. We have also the learning management system sort of course creator tool integrated into the platform, so that you can, as an author, you can, let's say, create an online course, an educational course, and sell it. Basically, we provide the tools for that. We have also integrated project management tool that you can use for your, let's say, project work. You can trace some tasks. You can change the status of the tasks. You can share the documents, share the PDFs, share the drawings even. So it's all inbuilt and can be used directly as a platform member. We have, of course, the private tutoring logic integrated, so you can schedule or you can get a tutoring scheduled, requested, a consultancy requested, and you can give this tutoring using the platform. You can request the tutoring using the platform. So basically, it's also another inbuilt feature. And the entire idea of starting as a customer and becoming as a partner, we call it a full cycle engineering. So basically, we support the entire cycle of, let's say, engineering, and this is why we call it full cycle sort of ideology. And now I would like to switch to the speaker introduction slide. So Cesar Menes Navarro is our today's speaker. I would like to welcome you, warm Cesar. Cesar is an aerodynamics engineer at Airbus Defense and Space in Tafe, Spain, where he contributes to the design and development of next generation military aircrafts. He holds a PhD in fluid mechanics from the Institut National Polytechnique de Toulouse. His doctoral research advanced the understanding of transonic buffet phenomena, morphing wings concepts, and turbulence modeling. Also, alongside his research and industry work, obviously Cesar is deeply engaged in teaching and knowledge transfer. That is why he lectures in thermodynamics and fluid mechanics at Universitat Karimani in Andorra, and has created widely used online courses already on Python-based CAD automations and also scientific visualizations. And his teaching journey has also included roles at INPT in Toulouse and Linköping University in Sweden, where he mentored students in CFD as well, and aerodynamics as well. And with his experience spanning programming, CAD, and CFD, Cesar brings both technical depth and passion for education to his professional endeavors. So I would like to welcome you again, Cesar, and the stage is yours now.
Perfect. Thank you so much for the kind introduction. Hello, everyone. Well, as Dimitri mentioned before, this is like the second part of our first webinar into scientific visualization. I'm going to start sharing my screen. Okay. Please let me know when you can see it.
Yes, okay. We can see it.
Perfect. Okay, as he was mentioning before, well, like 100% of the people who are here present, also who have answered the survey, haven't been in the first webinar, but don't worry, because like the previous webinar and this webinar will be like fully online. So even if you don't completely follow like through all the examples and all the theory, you can watch it again, like both webinars. And of course, feel free to send me a message like with questions to if you need like further clarification in some topics. Okay, so in this webinar, as you have already seen in the description, I'm going to focus entirely on the scripting part. And for this, I'm going to cover the three examples that we solved through the graphical user interface in ParaView. Okay, so my idea is that I'm going to execute each one of these scripts. We're going to see how the graphical interface is looking like, so what it has actually happened, and then we will like comment step by step which is the effect of each command. Okay, so let's go. The first one will be to visualize the pressure coefficient and the friction coefficient over the skin of an aircraft. Okay, so first of all, well, as you already know, this is the graphical user interface that we have seen in the previous webinar of ParaView. And the first step is how to actually run a script. So here in View, okay, we have the option to visualize the Python shell. Well, at the moment, it's not visible because I have it in another script. So you will click this, and you will have a terminal, a Python terminal that is looking like this, and you can actually dock it in any place of the graphical user interface. Personally, I like to have it here next to the pipeline, output messages, and so on. But for the sake of this webinar, I'm going to have it detached, because like that we can quickly focus on the terminal or completely focus on the graphical user interface. So the first step will be to execute our script. So I'm going to make it smaller. Okay, and the first will be like to visualize the aircraft surfaces. Okay. So what has happened? So here we have already in our pipeline two filters have appeared. One is the data that has been displayed with the pressure coefficient, and then another one that is displaying the friction coefficient, which is exactly what we did manually in last webinar, but this time it is fully automated. So let's take a look at the script. This is how it looks like. Okay, so the first step, it's obviously to load the dataset, because without data we cannot work. And for this, we are using a data reader. In this case, we're using the TechPlot reader. If you remember from the previous webinar, ParaView has a wide range of readers that can read the data from multiple CFD outputs. And if you are not so sure about which one to use, in this case, because I have generated with TechPlot, so I know that I have generated this data with TechPlot, I am using directly the TechPlot reader. But if you are not sure, there's a very good trick, and it's that in Tools, you can go to Start Trace. And with this, ParaView will start recording your actions in the graphical user interface, and then it will translate everything into Python. Okay, so you can press OK, and then you will go to one of your datasets. In this case, seminar material. Let's load once again the same dataset. Okay, I know it's TechPlot reader, so I will press OK, and then we will load the data as we did in the previous webinar. And then if we do stop trace, basically ParaView returns like a Python script with all that has happened, okay, between the start and stop trace. In this case, as you can see, like it prints a lot of information, and it is really important to understand why it's so what to take from this script and what to keep, because most of it is redundant, so it will just like add unnecessary complexity into your script. But I strongly recommend using this tool only for hand-picking very specific commands that you aren't unsure about how to do through terminal. So in this case, we have loaded data, and as you can see here, we have the command used for calling the TechPlot reader. Okay, so let's discard this. Let's delete this. Okay, let's go back to our example, and as you can see, well, so the first step is to load the data into our system. So we have the reader, we have assigned it a name, and then here we select which files we are reading from our hard drive. The next step will be to select which variables we want to set. So I'm going to just put this here. Oops. So I'm just to move this a bit so you can see it better. Okay, the first step is to see which variables we want to load. And as you remember, when you load a data set, when you go here in information, sorry, properties, I'm gonna make it smaller. Here in the reader, you can select or unselect some of the quantities, and in this case we want to import all of them. So for this, what we need to do is we need to provide in the surface data, we need to indicate which variables we want to load. Okay, because here what we need to provide a list with the variables that need to be loaded. And for this, if we know which variables has our data set, we can just create a list with different strings, or we can access like more indirectly to this information, to the stored, so to the available variables in our data set. Because if we get the property data array info, what we get it's a list with the variables that are available in our data set and if they have been loaded or not. Okay, so in this case all of them are loaded, and that's why. Oh,
So
yes.
Is it possible for you to increase a little bit the font size?
Oh,
We have
okay.
some-
Yeah, maybe he. Oh, I see. Oh, I haven't thought about that. I'm not sure if in the Python it's okay. I'm not sure if in the terminal it's possible here, so maybe I will just stick directly to the notepad. Can you guys read this? Is this better?
Yeah,
Oh.
I'm getting some likes for that.
Oh, okay. So sorry for that. Okay, so maybe I will just stick to the terminal in case, to the code itself. Perfect. Okay, so what I was saying is that first of all we need to go to a reader. We need to indicate in our reader which variables we want to import. So we need to provide a list with the variables that we want to load, and like this we can so ParaView will know which variables should load into the session. Okay, which will be exactly the equivalent of one second, I show it here, of clicking here the data arrays. Perfect. Then once you start a ParaView session, by default, it creates a view, which is called a render view, and we need to get a reference to it. So later on, we can display, hide, or show, or even split the views. So the first step is to get reference to this view. So for this, we use the method getActiveView or create to the render view, which is the one which is active. We can specify the view size, in this case, in pixels. So it's like a 2K resolution. We hide the orientation axis visibility and then the center axis visibility. Okay, these are like personal preferences, but it's like example like that you can manipulate everything in the render view. We set this view as the active one, and we also get reference to the layout because ParaView has layouts and layouts and render views. So you can create multiple layouts, and then within each layout, you can create a render view. You can split it again. Okay, so we will see like later on how to manipulate all this. But for now, let's hide that. So we get the reference to the layout, and then the first step is to display, to show the data. So this is our reader data, and then what we command is to display this data in the render view one, the view that we just got the reference to. Then we create a symmetry because we only have half of the aircraft, and for this we apply a filter which is called a transform that allows us to do like translation, rotations, or even scaling. And in this case, in order to get a symmetry, what we are doing is that we are scaling the geometry with the minus one in the y coordinate. So in this we get the symmetry. Okay, so like this we get these two shapes. Okay, and now the next step, because initially they look a bit like this. They look like this, but the next step is to add some color into it in order to visualize the interesting qualities. Okay, so the first is to set an adequate camera point of view, and for this, ParaView has 5 controls that I have summarized in this image. Okay, so first of all, we have the camera position, which is basically where the camera is located in the space. Then we have the focal point, which is where the camera is looking at. Then we have the view up vector, which is this vector perpendicular to the camera view. Then we have the parallel scale, which this will be like equivalent to the zoom control, which controls the location of the image plane between the point at which we're looking at and the location of the camera. And then we can select the parallel projection, which is a 1, if we want a normal one, so like orthographic projection, or set to 0 if we want the perspective. Okay. So we can play with these controls in order to select the view that we like. And then with render, what we do is we update the render view. No? So we update the display data. Now the next step is to add some colors. So for this, we're using the method getDisplayProperties, and we need to refer to the filter that we want to modify its graphical properties, and then where it is being displayed. Okay, so like this, we get an object that we call surf data display that will help us to manipulate these properties. Then, first of all, we set the kind of representation, because if you remember in ParaView, okay, we can select we can show the survey with edges if we want to show the grid. We can show points. We can show well, there are like different visualization styles. So we control that by setting the representation type, and then which is the color that we want to display. So for this, we're using the color by. Then we select the display properties that we want to modify, and then because we have imported point data, we are referring to points, and then we're displaying the value CP. If you are not sure about why here there is points, you can go to the first webinar where we have covered the type of data which is available in ParaView. Okay, so you are displaying it with the pressure coefficient. Okay, and then we are displaying this color bar, so we can visualize it in the render view, and then we set to true, and then we update the view. And then we do exactly the same, but for the symmetry. But in the symmetry, instead of showing the CP, we are showing the friction coefficient in the X direction. And then the next step, we can modify the color bar, because here we have colored the surface, but now we can modify the color transfer function to adapt it to interesting ranges. So for this, we're using the method getColorTransfer function, and then we refer it. So we set as an input the variable or the array that we want to control. Okay, so like this, we have the reference to its color transfer function. Applying preset, this basically means the color legend that we want to include. So imagine if we set CP again. So let's bring this back to surface. Basically, this will be applying the preset will be equivalent of going here and then selecting the preset that you like to have. Okay. So we have selected the preset, and then we select the number of discrete colors, which is basically, I'll show you one sec. Actually, I'm going to execute this because I think I touched a couple of things, and I'm going to start from 0. 1 sec, so I'm going to execute the material. Okay. The discrete colors, basically, they control how smooth the color bars are. So basically here, this is a color bar with 301 numbers of colors, and this is one with 11. So you can see, like, depending on if you want to see the color map more smooth or more discrete, you can control that by modifying that field. Okay. The number of table values. Then you can control the minimum and maximum values. And then the next step will be to control the location and style of the color bar. Because remember, like, so far we have colored the geometries, we have played with the color maps. Now we want to modify the appearance of this color bar. So basically, we need to we're going to use the method getColorBar. Okay, so we will get the reference. So the inputs are the color transfer function that we have defined previously, and in which render view we're going to show it. And once we have this color bar, we can fully modify all these properties. So the title, component, the orientation, all the ticks, which, if you remember from last webinar, will be the equivalent of going here, going to the color bar, and then modify all the properties here. But here, instead of going to the graphical interface and modify everything manually, we can set this script that modifies everything just by Python commands. So we have done that for the CP, we have done that for the CFX. And then the last step will be to save this image. Once we're happy with the layout, we're happy with the camera position, we're happy with the color bar, we can use the command save a screenshot. So we select, so we set the file name, then we set the image resolution and which view we want to save. Okay, and then after executing that, we will have in our post-process directory, which is here. Yes, we will have an image that looks like. Please open. Yes, an image like those that looks like this. Okay, so basically this is all the steps that we have done. Everything saved into a single image. Perfect. Okay, so this is the first example. Guys, do you have any question about this? Nothing was pretty simple. If not, you can watch again the video, and at the end we will provide all these examples so you can take your time to look at them. Okay. The next example will be to show the display. So to display the pressure coefficient over a wing slice, which would be the equivalent of solving this, doing this example that we did in the past webinar. Okay, so once again, I'm going to reset my ParaView session. I'm going to execute my script. Wing slice. Okay, and then we will briefly comment what has happened, and then we will explain it. So as you can see here, we have loaded our dataset, which is the complete aircraft. We have clipped it in order to avoid having the tail in our clip. And then once we have this clip, we can use 2D slice, so a plane, in order to slice the wing and get a 2D profile. And then we will use the plot on sorted lines filter in order to display the pressure distribution in another view. Okay, so how do we do this by using commands? So I'm going to skip the first part because basically this is equivalent to what we have done before. We're using the TechPlot reader in order to load all our data. We are setting a view that we are happy with. And then is when we start creating the filters. So first of all, we need to know the dimensions in order to know exactly where to clip. And then in first place, we're using the clip filter, which, if you remember, it's a filter that allows us to keep a given part of the geometry up to a given threshold. In this case, limited by a plane. So we're using the filter clip. So we put a name that we are happy with, and then we are applying it to the surface data, so which is the input to the filter. We set the clip type, which is a plane, and then we set the origin and the normal of this plane. In this case, is the 80% of the fuselage in the X direction. So like this, we chop our fuselage and then we get our clip. Then the next step will be like to do the slice on the wing. And for this, we're using the filter slice. In this case, the input is the body clip that we have done previously. And this time the origin is on the half wing. Okay, so wingspan will be the whole aircraft span divided by 2. So we want to do it at half of this span. Okay, and then the normal, it's the y-axis because it's because it's like it should be normal to the y-axis. And like this, we have our first step. So I'm gonna do it here because it's gonna be like much nicer to see it. Well, I'm going to hide the plane. Okay. So what we have done so far will be has been this. Because here, let me just change the coloring. Full. Okay. And then let's increase the line width. Okay. So far we have done the following. We have loaded the data, and then slice the wing. Then the next step will be to split this window and then create a XY plot so we can visualize this data. And how do we do this? So we will go back to our code, and in order to create a new window, we will use the command split vertical. Okay, so we will get the reference to the layout that we created. We split it, and then we need to include which index we have to split, because that's the way it works. And in order to know which index we need to use, we can use the method findView. So this is the name that we set to our render view object, and then the output we bring it to get view location, which is a method within layout. So like this, we can get the index in the index split, which is the index that we want to split. So we're splitting the render view 1 by 30%, and then we create another view, which is a quartile chart view. We don't show the legend. We can control here the X title and the left axis title. And then once we have created this view, we need to assign it, because by now it's an object which exists in our workspace, but we need to use the method assign view to layout. So we select which view within which layout. And like this, and then later on we can rename the view. So as you can see here, what we have done is we have taken this render view, and then we have split it by 30%, and we have placed a secondary view, which is our XY plot window. Okay, and then once we have created this secondary view, we can create our filter, plot on sorted lines. We set our name, we set the input, which is the wing slice that we have created before, and then we start playing with the properties. So we want to show it. So we want to show this filter in the line chart view that we just created, and here we control. Well, we don't want to use the index for the x-axis. We want to show the x coordinate, and then we set the label and which series we want to visualize, and the thickness of the line, and then we update the render view. Okay, and then we have already seen. And then if we want to export data, which is quite useful, what we can do is we can use the save data method, and for this we select a file destination. As a proxy, we select the filter from which we want to save its data. We can choose which arrays we want to write. In this case, well, it's the only one, CP, the precision, and if we want to use scientific notation or not. And then as a result, we will have in our work directory, sorry, one sec, it should be here. We will have this file created, which is a CSV with the X, Y, and Z coordinates, and then the pressure associated to each one of these points. Perfect. Like this, we conclude the second example. Guys, do you have questions about this example that we can cover? Okay, if not, we can. If not, you can think about them, and then you can ask them to me at the end.
I think we have in the chat question.
Oh, okay. Did you get to know what methods for recording trace? So I personally I get to know most of them by using the start, trace, and stop. But it was a lengthy process, because I think I learned like 80% of what I know by doing that, but it's true that very specific commands are not fully covered with the trace tool. And in those cases, I had to either ask in forums or go to the documentation. But I would say like 80% of applications, yes, you can do it through the start and stop trace. Why do we need a clip of example? Yes, so basically in this case, we need the clip because let's show this. Okay, because imagine let's show the whole thing. Because at the moment the slice is at 50%. But imagine that we want to do like multiple cuts and we want to only slice the wing. If we do like a cut near the root, it will also slice the vertical tail, right? So by isolating the wing, we avoid having like a secondary cut in the tail. Okay. I guess that's clear.
Thanks to that. And we have also a raised hand from Mohammed. I will unmute him.
Yep.
Yeah. So go ahead.
Hi, Cesar. Hi, Dimitri. Actually, since this is my first webinar, I actually participate in this webinar. I have no idea about the ParaView, but if I'm not mistaken, this is just post-processing software, right?
Yes.
Not, there is no solvers inside, and we just we can use for post-processing as well, right?
Exactly. Mm-hmm.
And the important, I actually, as a designer, we usually like to work with data, not in terms of view or rendering. I'm not very interested in the these. Actually, this is not very useful for me, but the data is much useful because when I have these data, I can actually filter the data, do some post-processing regarding this data. Is there any filtering, a specific filtering for data particularly? Actually, for example, I want to filter all, for your example, I want to filter all CP between these, between A and B. Okay?
Yes. Yeah, so basically I think that it was meant to be like a more introductory webinar, but obviously you can do all this. So for instance, I'm going to show you like a bit some more complex examples that we can work with. So basically, this is an example of how you can use scripts to systematically extract the data. So by this, you can study the pressure distribution in different positions of the wing. Or for instance, this one. This is another example in which what we have done is we have taken a CFD simulation, and with ParaView and some scripting, what we have done is we have isolated each one of the components of the car. So what we are doing is that we are showing a cumulative distribution in order to visualize how each component adds downforce as we advance in the car. Okay, so I just didn't want to get like super into this because it's like a webinar for starters, but this is the kind of data analysis that you can conduct once you're like familiar with scripting in ParaView.
Sure. Gotcha.
Yes. So, I mean, I agree. It's like data is key in order to conduct analysis and do conclusions in order to move forward with other designs. But the way you extract the data and the way you classify the data visually, like this one, it's essential. So sometimes it is quite convenient in order to know scripting in order to extract this data efficiently. And if you have, let's say, 50 designs like this one, and you want to consistently compare them, it's great to have like one single script that will run through all your simulations, extracting the same data, and you can compare consistently each one of your designs in order to compare them.
Yeah, exactly. The point is actually as a designer, we change the load case. For example, we need to change the load case, and we should compare the output with the input. If the output is not in our favor, we should change the input. For example, changing the wing cross section and so on. So, is it possible to connect the ParaView with another software? For example, since you have not solver inside, so is it possible to connect this software with another software in order to actually simultaneously get output from ParaView, get input from another software, and then we actually do in the for loop design actually implementing? Yeah.
Yes, for that, I would strongly recommend you to look into ParaView Catalyst. So basically, this is a branch of ParaView that I am not familiar with. I'm not an expert on that, but I'm aware that you can integrate, because again, like ParaView is open source. Basically, you have all the source code available, and you can modify it, tweak it in order to adapt it to your server. And you can actually like post-process in real time, feed data and so on. But that's extremely complex. Once I was assisted to like some lectures in Universidad La Sapienza in Rome, and the guys have developed a CFD code, again, which was DNS, and as the simulation was being executed, the post-process took place within the program itself, right? So basically, they had their solver and ParaView fully coupled, and they were simulating and post-processing everything in real time. So yeah, that's possible, but that requires some developer knowledge. So I think we're drifting away from the topic. I think we will try to go back to it. But thanks so much for the questions. And if you have more topics that you want to discuss, please you can send me an email or a message on LinkedIn, and we can see more about this. Okay.
Yeah, I agree.
So yes, let's go to the third example. Okay. And in this one, we're going to see where are we? So for this, what we're going to see is how to compute the aerodynamic forces over a wing. Maybe like you remember this the example. It was a bit complex, but I'm gonna try to explain it a little bit more in detail during the scripts. Okay, we still have like 20 minutes, so I think that we are still having time for this. Maybe one more example. Okay. So let's execute the script. These are the coefficients. Okay. So as you can see, let's zoom in. Okay. So this is our wing. If you remember, like each one of these arrows are the pressure forces that the fluid is applying into the wing surface. So basically, the length of each one, it's proportional to the pulling. In this case, it will be like a pulling force, and in this case, will be like a pushing force because it is acting against the wing surface. Okay, so let's go to the script. So once again, load dataset. I'm going to skip it. We have already our data loaded into ParaView. Then, in order to compute the aerodynamic coefficients, we need to non-dimensionalize the pressure forces by a reference pressure, or by a reference force, which in this case is the dynamic pressure times the aerodynamic, times the reference surface. And since we already know, so for the pressure forces is the integral of the pressures of the pressure over the applying surface. But since we don't have an analytical solution for this integral, we are doing the summatory of the small contributions of each cell into the whole surface. So we already know the reference pressure, we know the dynamic pressure, we have the reference area. So the only term missing is the summatory of all these little forces that we're going to see in ParaView how to do it. First of all, we'll create our first filter, which is a calculator. in this case, it will be applied over the wing's surface. I will call it pressure E, so the if pressure. And what we're going to do is we're going to subtract. So press, it's a variable available in our data set. So we're going to subtract the reference pressure to this. Okay, so like this, we'll have an idea. So we'll have the delta of pressure and the idea and the sense if the pressure it's pulling or pushing the element, depending if it's negative or positive. Then we will use the filter generate surface normals that will allow us to get unitary vectors in the normal to the surface. Let's quickly visualize them. Okay, generate surface normals. Is this? Oh, no, sorry. We generate the surface normals, but then we need some glyphs to display these vectors. So I'm gonna just do it in solid color. Okay, so what we have done is we have generated unitary vectors that are normal to the surface, right? And then later on, what we will do is like we will multiply. So we will scale these vectors with the force, which is the pressure times the area of the element. And like this, we'll have the magnitude and direction of the force of each element. So we have done this. This is just to generate and display the number of vectors. Then we use another calculator in order to compute the pressure forces. You know, the pressure is a force times a surface. So therefore, the force will be the pressure times the surface. Okay, so for this, we're multiplying the local pressure, which is a scalar value, times normal. So this will give us the orientation of the force. But at this stage, we are not multiplying the area because, as I explained in the previous webinar, in the area is multiplied later on in the integration filter. Okay, so the next step will be to integrate all these variables. So we're using the integrate filter. Our input is the calculator that we have defined previously. And here it is important to set divide cell data volume by, so we set this to 0 because what we want to have it's this term, okay, which is phi. So where phi is the pressure times the normal. But this filter by default takes the values, so takes the arrays in the dataset and multiplies them by the local area. So that's why if we do this, the problem is that we are multiplying here the local area, and here we are multiplying once again the local area, and we don't want that. So that's why we skip here the multiplication, because we know that the integrate variables will multiply this by the local area. And here we set this to 0 because we don't want to divide it by the local area, because if we do so, we are not doing an integral, we are doing the area weighted average of an array. Okay, so these are the way you compute it. So with integrate variables, you can either obtain a summatory of a field or obtain the area weighted average. Okay. So we have done this integral, and then how do we access to these values in command line? So for this, ParaView has a very interesting command, which is fetch. So we need to go to ParaView, Server Manager, fetch, and then we need to set the filter that we need to get the reference to. So we're using, and then this command, so up to here, what gives us, it gives us the VTK object that is being pointed by this filter. And once we have the VTK object, again, if you don't know what VTK object, go to the previous webinar because I covered what a VTK object is. And then once we have the VTK object, we can access to its properties, so we can get its point, the point data, because we know it's we have imported point data. We can get its array. So this will have the name that we have set before in the calculator, and then we know that it's a 3D vector, so we get the value. So we get the value in the X, Y, and Z components, because this this array has 3 components. And then now we have already this term, which is the summatory of the pressure forces. And then we can non-dimensionalize it with the dynamic pressure times the reference area. And like this, with this, we get the pressure force coefficients. But if we remember from the previous webinar, these forces are given in the Cartesian axis, so in the x, y, and z coordinates. But this, in this case, the wing is flying with an angle of attack equal to 7 degrees. So we need to rotate we need to rotate we need to rotate the force components with respect to the wind's direction. So for this, we're using a rotation matrix in the y-axis, and by doing the dot product between this rotation matrix and the force components, we can get the aerodynamic coefficients that we have previously printed when we have executed the script. Okay, so like this, with this script, you can easily compute the pressure forces over multiple surfaces. Okay, guys, do you have any questions about this one? Is everything clear? Yes, maybe not. Okay, then maybe I will just continue to the next, to the last example of this webinar, which is new. And actually, this example was inspired by one of the attendees from last webinar, who was asking about how it's possible, like, to modify color maps. Okay, so I'm gonna try to address this question. So let's execute this script. Share image. I'm gonna hide this, the last one for now. Okay. Oh, my computer froze. Amazing. Oh, good. Perfect. Okay. So what am I showing here? So I am showing so this is an airfoil is flying a transonic regime. We are studying a shock wave. And then what I'm displaying here is the density gradient. Okay. So we're going to see how to obtain gradients of scalar fields. So let's jump to the next example. Okay, once again, I'm going to skip the load data phase. Here, I am using a calculator in order to build our velocity field. Okay, so we multiply the scalar components with the corresponding unitary vector in order to give the direction. In this case, the y component is 0 because it is a 2D case. And then what we do is we use the gradient filter, which has multiple utilities. So we set as an input this velocity calculator. And within the gradient filter, we can not only compute the gradient, but in case we have like vector fields, we can compute the divergence, we can compute the vorticity, and then we can compute the Q interior, right? In this case, what I've done simply, it's I just compute the density gradient in this case, and then as we have seen previously, I displayed it with a grayscale, and I adjusted the transfer function in order to make it more visible. But here the interesting thing will be the vorticity and how to manipulate slightly the color map in order to bring the attention to the elements that we want to highlight. Okay, so up to here, the vorticity, this is something that we have already seen before. So gradient, we compute the vorticity, and then we have the vorticity available in our dataset. And then because it is a 3D vector, we want to show the vorticity in the y direction. And then here, what we're going to do is we're going to modify the color map in order to add the transparency. So let's go here. So this is the vorticity. And then as you noted here, as you can see in this color layer, what I've done is I've left this range in the middle completely invisible. Okay, because usually, like when you are inspecting a vorticity, you are interested in the extremes, and you don't really care about the intermediate values. And for that, you can just like simply hide them. And for this in code, what you need to do is once you have the once you have the color transfer function that we got before, we need to enable opacity mapping. Okay, so once we have that, we need to get the opacity transfer function of the vorticity, and then we need to select the points. So we need to specify some key points. I have explained them here, but maybe we can just we can better go to the terminal, to the graphical user interface, and then see them in a much clearer example. So basically, the points that we have specified in the script are basically these points. Okay, so depending on how we move them, okay, we can play with transparency, right? So if we want to highlight or highlight some, we want to ignore what happens between this point and this point, we bring the visibility to 0, and then we can maybe adjust these values in order to have this abrupt change. And like this, we are increasing, we are targeting, so we are like focusing our analysis in the areas that we are interested. And imagine that we want to hide the high regions, the high value regions. What we can do is we can maybe create an extra point. We bring this one down. Okay, we bring this here. So what happens is that we have set visibility from this value up to the maximum value, and beyond the maximum value, it is invisible again. Okay. Was that the question? Oh yeah, Juan David. I think like he wants to speak. Yes.
I have a question. You say us later before that you choose some key points that represents on the profile. How do you choose that key points to represent now with the forces, with the pressures? Yes.
Yeah, sorry, I think I didn't get the question. Like, you mean like the key points for the color bar, or
Yes.
the key points?
Yes, the key point for the color bar. How do you choose it, or how do you?
This was an example. I mean, so what I've done here. So basically, there are like, so I set a minimum range for the vorticity, a maximum range for the vorticity, and then I decided to hide like 75%. In this case, was completely arbitrary because I just wanted to illustrate you guys like how to do it. But this is not, how to say, these specific example or values are not very relevant, just to show how to create the opacities.
Oh, it's okay. Thank you.
Yeah, welcome. Okay. Yeah, but like if there's like some terms that are unclear, like each one of these terms, it's explained here. Okay, and I think basically that's it. That's all what I wanted to cover today. I just want to mention that I'm going to also, so once these data and examples are distributed, I think Dimitri will send an email with the links to download this data. I have also provided one last Python script in case you want to explore a bit more in how to extract and query data. So basically, this is like how to, for instance, get the information from the pipeline, get some information from by using the fetch tool, getting number of points, get like multiple. So like multiple examples on how you can extract valuable information in order to understand your data set and decide what to work on. And maybe just one last thing I wanted to show. It's well, I already like showed some examples before when Mohammed intervened, but up to now I think that we have just covered very simplistic approaches and very simplistic examples, but I wanted to show what you can achieve once you are like quite proficient with scripts. So, well, we have already seen this example. You can programmatically extract some slices of pressure. You can deeply analyze the force over wing for sport cars aerodynamics, and then isolate each one of the components. You can, through scripts, also like do all the slices that you want. And with I've done this by using the same opacity techniques that we just explained before, so that I can do like multiple slides. I just set some key parameters, and then from above that parameter, everything is invisible for me. Then if we want to study the boundary layer over a week, we can also create some lines. And then from these lines, we can extract the unstable data, as I showed in example 2. And then because we have all the data in Python, we can create all these layouts. And also, you can go even beyond, and then you can work with animations. So this is an animation that I did recently, where basically I was presenting a research paper that I did with one of my colleagues. So you can see, like with ParaView, you can like show, display all the computational domain. You can show 3D views. You can display 2D street lines, and then we're now showing a tuner to show a comparison between two cases. Then now we are zooming back into the case, and then we're displaying the grid. So once you get proficient with ParaView, you can do all this, because all this that is displaying in the screen is done by using scripts. And also another video that I wanted to show, and this is the last one, I swear. This is another case that I did with the scripts. So what I'm showing is I am showing a car, and then what is happening is that I am transforming the track. So I am displacing the track to make it appear like it is moving. And then we have some bars that are moving around the car, and then I am showing the streamlines. Then when it reaches that position, I am showing some cut planes in order to scan all the flow around the car. And then when it reaches the end of all what I wanted to show, it takes a turn, like if it was drifting. I think it will do a turn now. Okay. So yeah, so basically when you get familiar with scripting, you can do like basically everything. Because with Python, basically you don't have any limits and you can do whatever you want. Now, the next step that I wanted to target on is on GPU rendering, because this is like CPU rendering. And my goal is to get more into the realistic rendering. Okay, so this is everything from my side. If you guys have more questions, please feel free to make them.
Thank you so much, Cesar. I think we have one from Mohammed Ozan.
Yes, exactly. So plotting the Q criterion. So first of all, what I will do is I will go into this gradient filter. Gradient filter. I will set this to 1, the Q criteria. And then there is another filter that I haven't covered yet, but it's a filter which is called contour. Okay, and with this contour, you can create a visualization of this Q criterion. I have here an example. So this is another case with the scripts. So basically, what I'm showing here is I am showing the Q criteria of the velocity the Q criterion extracted from the velocity field, and I have colored this contour by using the velocity magnitude. So yeah, so it's a way to display the Q criterion.
Did it answer your question, Mohammed? Yeah.
Okay. Perfect.
Perfect. Yeah. Thanks a lot, Cesar. Once again, I will quickly switch to the last slides of this webinar.
I will stop. I will stop sharing.
Yeah. So I will share my screen now. Yeah. As mentioned by Cesar, yeah, we will share all the materials, also the recording after the webinar, so you'll get an email with the content of today, so you can get back to that and do all the processing and exercises offline on your side and repeat the exercise. So basically, you have also multiple options how to move on from that webinar. You have also some of very interesting CFD and CAD related online courses on our platform. And for every attendee, you will get discount code that we will issue after the webinar, White 10. Basically, you can use it for every purchase on the platform, getting some course, getting some tutoring as well. So if you have a particular issue with your Python script or with the processing of your data in ParaView, you can take a look at our tutors on the platform. You can try to schedule a session with them and get through all of that issues and your particular exercise and your project together and solve everything that are your current concerns in the project. So basically, these are the main links, the main URLs, White.com courses and White.com members. And do not forget to use that discount code to get 10% off. I think that would be it for today. Any final words from your side, Cesar?
No, other than thank you so much to the attendees and for the interesting questions that they did during the session. Thank you so much.
Yeah, thank you so much. Also from my side, to our speaker, to Cesar. That is very insightful as always, I would say. So it was sort of a part 2 of the previous one, and you will also get the previous webinar recording if you explore a little bit on our website, on our platform. There is a section or URL called webinars, and you can see the previous recordings also as well if you're interested in that. So yeah, thank you so much, Cesar. It was a pleasure,
Thank you.
as always. And thank you, dear attendees, for having some time to tune in. We are also happy to have you on board, and we will meet you in the next one. Thank you so much.
Thank you so much, guys. Bye-bye. Ciao.
Bye-bye.